Welcome to this lecture on basic analysis of vibrations by DHS MaithripalaDHS. So let's take a quick look at what we mean by vibrations, what we intuitively understand by vibrations. So over here you see 4 types of motion. On one hand you have this oscillatory motion. On one hand you have this circular motion, again an oscillatory motion, again an oscillatory motion. Out of these, which one do you typically associate with the word vibration? So what is common in all of these things is that all of these are periodic motion. So this is periodic motion, the motion repeats itself over and over again. This is periodic motion, motion repeats over and over again. This is periodic motion, motion repeats over and over again. And this is periodic motion. So out of these things, which one do you typically associate with vibrations? So even though this is periodic motion, we don't typically call this vibrations. This one also, we typically refer to this as an oscillation and not as vibration. This maybe we might call it vibrations, but well, the most natural thing to think of this is as a oscillation. On the other hand, this one we typically will refer to as a vibration. So typically what we mean by vibrations is high frequency oscillations or high frequency periodic motion. The most basic form of vibrations or periodic motion is simple harmonic motion. So let's take a quick look at that. So if you have a spring suspended on a mast and you just pull it and let it go, and so it will go up and down like this, and if there is no damping, what you will notice is that if you map this point, center of the mass, to the circle and see how that point moves on the circle. So you map this point to the circle and see how it moves on the circle. What you will notice is that that point moves at a constant angular rate. So therefore, the displacement will be given by something like this. A sinusoidal function of the angular rate of rotation of that point will correspond to the displacement of this. So this is a very amazing thing. On the other hand, if you apply Newton's equations to this spring mass system, you will end up with a differential equation like this. M times acceleration is equal to the spring force minus kx. And what is interesting is this is a mathematical object. So we have used laws of nature to model the system and arrive at a differential equation. And what we find is that the solutions of this differential equation are also given by functions like this. So we have an agreement between physical observation through this circular mapping into the circle, and through laws of nature, we arrive at a mathematical object, and the mathematical object predicts that the system behaves like this. So this is actually the art of science. So we have physical behavior on one hand, and we have laws of nature on the other hand. So laws of nature give you a mathematical concept that describes a physical behavior. This is what we will try to adapt in trying to understand vibration. First of all, we'll look at what the sources, typical sources of vibrations are. I think all of us have felt what we mean by vibrations, and we have this intuitive notion of what it is. And mostly we would have noticed it near rotary machines, in a bus, in a vehicle, near fans, near blowers, near air conditioners, coolers, and near lathe machines, and anything that has a rotating part, we would notice that there is a hum or there is a vibration that you would be feeling. So if you just try to understand this from a very simple point of view, this foundation can be thought of as being on 2 springs, and the structural damping of the foundation can be thought of as a shock absorber or a damper. And this whole setup that is sitting on the foundation can be thought of as a big mass, and the rotor of the motor and the fan that is coupled to this can be thought of some rotating disc. Now what happens is, however hard you try to align these things, it is impossible to to align this rotating thing at the center of its mass. So there's always an eccentricity between its center of mass and its pivot point, the point of rotation. And what is the result of that? So when this motor is spinning at a constant angular rate of omega, what that means is this, due to this off center of the center of mass, the pivot point will feel a centrifugal force in this direction that is equal to m times E times omega squared. So that is what we have over here. So the vertical force that this system feels is something like a sine omega t. So because of this is omega t, the vertical component will feel sine omega t, the horizontal component will be cos omega t. So this system will feel a vertical force, something like this. And so this is the source of vibrations in most of the cases. So you have a physical system that has a rotating part, it has an eccentric mass, and due to the eccentric mass, the system will feel a sinusoidal force acting on it. Let's take a closer look at this using this the art of science that is trying to model this behavior using mathematical objects. So we apply Newton's equations to this simplified model of this complicated system, and we arrive at this expression over here. The total mass times acceleration is equal to the spring forces plus the damping force plus the external force acting on this due to the rotational unbalance of the rotors. And now if you just divide this whole thing by m plus m and call k over m plus m as omega n squared, define theta as this. So in other words, 2 theta omega n to be c divided by m plus m. This differential equation can be converted into this form over here. And so this is a very simple second order linear differential equation. So what we see is the laws of physics, or in other words, specifically Newton's laws, have allowed us to describe this system as a second order differential equation of this form. So the solutions of this second order differential equation will sufficiently accurately, or to the approximation of this model, describing the behavior of this. So the behavior of this system can be thought of as given by this differential equation, and since it's a mathematical object, you can find the solutions of that. So the solutions of that will correspond to the physical behavior of our system. So let's try to look at these solutions of this and try to get some understanding about the physical behavior of our system. And so here Ft is a sinusoidal force due to the rotational unbalance of your system. Let's first consider the case where the rotary part is not rotating, or the motor is switched off. In that case, F is 0, and we'll consider the case where the damping is small, or it is between 1 and theta. And when you can use Laplace transforms or any other method, and you can find that the solutions of this differential equation when the external forcing is 0 is given by something like this over here. So this is actually part of your assignment, and assignment number 2. So please go through the lecture notes and also and try it out on your own, and you will find that the solution of this can be written down in this form. And where this omega t is given by this expression over here. And if you sketch this one, or if you plot this one, you will see that it looks something like this. So you have a sinusoidal term with amplitude that is decaying exponentially, and that exponential decay is given by minus theta omega nt, and omega d is given by that. So let's take a closer look at that. So when you solve this differential equation, maybe using Laplace transforms or any other method, you will always run across this characteristic polynomial of this system. So this system has the following characteristic polynomial, and if you look at the roots of that characteristic polynomial, minus lambda 1 and minus lambda 2, the roots play a crucial role in the behavior of the system, and that's why you call it the characteristic polynomial. So the behavior is completely given by the roots. So you will notice that omega d, theta omega d is the uh, so I omega d, I think. Sorry about that. There's no theta there. I omega d is the complex part of it, and the real part of it is minus theta omega n. So the minus part, the real part governs the decay, and the complex part governs the natural or the oscillations. Let's similarly take a look at the situation where now you have a rotary part and unbalanced mass, and therefore a sinusoidal force acting on your system. And again, you have been asked to show that under these conditions, that the solutions of this system are given in the following form. And one of the ways that you can do it, you can use Laplace transforms to transform this differential equation into a transfer function form. So you will have x of s times this times that. So that is the Laplace transform of this. And this thing is what we call typically the transfer function. And if you take the inverse Laplace transform of this, you can show that the inverse Laplace transform corresponds to something like this. And where this term over here is given by the magnitude of the transfer function with s replaced by I omega, the forcing frequency. And the phase is given by the angle of the transfer function with s replaced by I omega. So if you again look at what they are for different values of theta, you get something like this. This is for the amplitude of the vibration, and this is for the phase shift of the vibration. So what does this tell us? This tells us that in steady state, when you have a system that is like a spring mass damper system, forced externally by the sinusoidal force with frequency omega, your steady state response is also sinusoidal. That is very interesting. So you force your system sinusoidally, your steady state response is also sinusoidal with two differences. Your amplitude is magnified and your phase is shifted. The magnitude of the amplitude magnification depends on the frequency, and that frequency behavior is given by this expression over here, and if you plot it, it is given by that. And the phase shift, it also depends on the frequency, and if you plot it, it is given by this for various damping ratios. And so what you notice is there is a particular frequency at which the amplitude of vibrations becomes very large. Or if the damping is zero, the amplitude of vibration becomes extremely large, and that is what we call resonance. So in the undamped case, amplitude will grow infinitely, and that's what you see over here, these two curves. But for finite damping, the amplitude will not become infinite, but it will reach a maximum value, and that is what we call the resonance frequency. And so the resonance frequency is given by this. So if there's no damping, the resonance frequency is equal to the natural frequency of your system, and this maximum value is also given by that. So thank you. We will continue this discussion later.